Conservation of Momentum by Dr. Clyde Letzum. In this video, what I would like to do is to first start off by defining what is momentum. And then from there, we'll take a look at a system in which we have conservation of momentum. So let's go ahead and begin. So momentum. Momentum is the product of mass times velocity of an object. That is, P is equal to M times V, where P is momentum, M is the mass of the object, times velocity of that object. Since velocity is a vector quantity and it makes up the momentum equation, or momentum, then that means that momentum is also a vector quantity. And so whenever we express momentum, we need to not only talk about the magnitude of momentum, but we also need to talk about the direction of momentum. When it comes to the units for momentum, in the SI units, momentum is expressed, or the units for momentum is kilograms times meters per second. Now, that we understand a little bit more about momentum, how did it possibly come about, the equation for momentum or the discovery of momentum? Well, it may be traced back to Newton's second law, which states that F is equal to ma, which is force is equal to mass times acceleration. Now, if you recall, acceleration is equal to velocity divided by time. So the force is equal to mass times acceleration equation may be rewritten as force is equal to mass times velocity divided by time. And if we multiply both sides by time, we see that we have force times time is equal to mass times velocity. And so therefore, force times time is equal to the momentum. Okay, so now that we understand that, let's go ahead now and talk about conservation of momentum in a given system. When we say that we have conservation of momentum, what we're saying is momentum is conserved in a system when the total initial momentum in that system is equal to the total final momentum in that system. Written in equation form, that is to say then that the initial momentum, total initial momentum, is equal to the total final momentum. Written a different way, the initial momentum of one object in that system plus the initial momentum of a second object, so on and so forth, until we get to the initial momentum of the nth object. If we sum all of those up together, that should be equal to the final momentum of the sum of all of those same items. Okay? Okay, and so that again would give us conservation of momentum. That is conservation of momentum. All right, so now let's look at an example. So in this example, we have two carts. These two carts are initially next to each other on a track. They push away from each other and hit two rails at the ends. In this example, we want to find the ratio between the distance both cars traveled if they hit the rails at the same time. Okay, so in order to figure this problem out, we're going to have to use the conservation of momentum equation. Conservation of momentum again is equal to summation of the initial momentum is equal to the summation of the final momentum. And so for this system here, then that would be the initial momentum of the blue car plus the initial momentum of the red car is equal to the final momentum of the blue car plus the final momentum of the red car. Okay, expanding that out, meaning that we're going to write m times v for our momentums. That gives us the following equation here, where this portion right here represent the momentum, the initial momentum of the blue car. This portion here represents the initial momentum of the red car. This portion here represents the final momentum of the blue car. This portion here represents the final momentum of the red car. If you recall from the initial problem, we stated that the velocities of the two cars, remember, was zero because they weren't moving. So because of that, then we may replace the velocity, the initial velocity of the blue car and the red car with zero. What this leads to then is that we have 0 is equal to mb times vbf plus m times vrf. So what that's saying then is that the initial momentums are equal to 0. And then in this case, then that what this is saying is then is that the final momentums, pardon me, should be also equal to 0. And so because of that, then we may rewrite the equation such that we have negative mb times vbf is equal to mr times vrf. Now what this portion here is saying is that in this case, the velocities of the cars should be heading in the opposite direction. Okay, the velocities of the cars should be heading in the opposite direction. And that's what this negative sign right here in the front means. Okay, now given that that's the case, let's take a couple of notes. Let's pay attention to a couple of things here. We know that the velocity is equal to, because remember we're trying to find the ratio of the distances traveled, right? The velocity is equal to x divided by t. We also know that the blue car is heading in a negative x direction. Because the blue car is heading in a negative x direction, what that means then is that this v right here will be a negative value. Okay, that will be a negative value. So when we put that negative value in, that negative value and the negative that we have here in the front of the this portion of the equation, then those negative and negative, remember, becomes positive. So we end up with the equation m sub b times v sub bf is equal to m sub r times v sub rf. Okay. All right. So now, given that that's the case, all right, let's go over to our new page here. And we also know, remember from our note before, we can replace our v's with x divided by t. And so that's what we did here between this line and this line. We replaced our velocity with the displacement divided by time, which is the equivalent of the velocity. And our new equation now becomes m sub b times x sub bf divided by t sub bf is equal to m sub r times x sub rf divided by t sub rf. So what this is saying is that the final momentum again of the blue car should be equal to the final momentum of the red car. Okay, again, they're just going the opposite direction, but we've already taken care of that portion in the previous slide. So given that that's the case, then remember that we said that we want the two carts to hit the sides or the rails of the track at the same time. Because the two cars are going to hit the rails at the same time, that means then that this t and this t are equal to each other. And so we may eliminate both of those t's, and therefore then our equation will then become m sub b times x sub bf is equal to m sub r times x sub rf. Okay, and from there then, since again we're looking for the ratio between the distances, we may manipulate the equation so that it becomes the following: m sub b divided by m sub r is equal to x sub rf divided by x sub bf. Okay, so what this is saying then is the ratio between the red car and blue car should be equal to the mass, the ratio of the masses blue car divided by the mass of the red car. So this is our final solution here for the problem where we're looking for the ratio between the displacements of the two cars. Okay, so in this video again, what we looked at was momentum, and conservation of momentum. We defined momentum. We defined the conservation of momentum, what it means, and we looked at an example. Please do visit my YouTube channel for additional uh, examples, physics examples, and electrical engineering type examples. My YouTube channel information is listed here at the bottom. You may also look at my website for additional information on different lectures on physics and electrical engineering type problems. Thank you.